Hello, everyone. My name is Aurelio Reis. I work with NVIDIA, and I'm here to tell you about how to optimize your HDRP renderer. So, who am I? Engineering director at NVIDIA, primarily responsible for the graphics developer tools. So that includes Nsight Graphics, Nsight Aftermath, and if you're familiar with the Switch tools, we make those as well. So in a previous life, I was a game developer, and yes, I used Unity. Who doesn't, right? So I'm quite familiar with it. I want to start by asking the audience a few questions. First, how many develop here primarily on the PC? Good number, okay. How about console? Okay. Years of Unity experience, less than one, kind of newish. Okay. 5, less than 5? Okay, greater than 5. Wow, okay, that's great, a lot of experts here. How many consider themselves graphics programmers? Okay, what about technical artists? Interesting, okay. And last question, I swear, how many of you actually know about Nsight Graphics? All right, that's fine. I'm going to teach you a little bit more about it today, so hopefully everybody can raise their hands at the end of it, become pretty familiar with it. So let me tell you a little bit about what we're going to talk about. So the agenda today, entering the world of high-performance graphics. Let's talk about what that means, how HDRP is important to that. We're going to talk about the basics of graphics debugging. Sounds like that's kind of a new concept to some of you, so I want to make sure that you understand the basics and before we dive into a little bit more advanced topics, including profiling. I think that's why most of you are here. You want to understand how to make your applications run faster. So after we go into advanced profiling and optimization, let's talk about those next-gen debugging tools. So there's a lot of great new stuff that NVIDIA has enabled with the Turing architecture, and we specifically want to make sure that there's a good ecosystem, a good way to develop for those new features. And then finally, what's next, both for you and for us. And then we'll wrap up and do a Q&A. So hopefully you have some good questions that you're thinking about writing down for the end. So, the world of high-performance graphics. What does that mean? Unity is moving towards more customizable renderers. So you can actually take HDRP and be able to do some interesting things with it. Why is that? Higher fidelity graphics is the most obvious thing. We want consistent high quality for high-end platforms. So you have Xbox One today, you have Xbox Next tomorrow, and you want to make sure that you're developing things that work not just for PC, a high-end PC, but for these new next-gen consoles as well. In some cases, you can treat them similar, but they are very distinctly different. HDRP enables that entire concept. Better control of performance, so you can understand when you're not getting what you need, those limitations on your performance, and be able to improve on that with more direct control with HDRP. Exposure of cutting-edge features, DXR being a pretty big deal, Vulkan ray tracing as well. Variable rate shading, all these other really cool technologies that are coming online. Being able to have more control of the render allows you to get exposure to that, including compute shaders, which are very, very powerful. And finally, unique aesthetics and graphic styles. So, Breath of the Wild is a very unique-looking game. It's not quite toon shading. What if we all use the same toon shader? It'd be kind of boring, right? Being able to write your own render allows you to customize that look and create a new visual fidelity that defines more of the spirit of what you're trying to achieve with your applications. And so, very quick overview. It all started with the scriptable render pipeline in 2018.1. From there, you kind of have this evolution where, as was announced yesterday, it's now called the Universal Render Pipeline, being something that's very performance-centric and something that you can use very quickly, and then also this other path, which is HDRP. We're going to talk about that today. It's about cutting-edge, high-fidelity graphics, and that's what we want to help you enable. So HDRP, really quick overview, uses a C# scriptable render pipeline API, so there's some source code on the side there. You can actually see one of the sample high-definition renders. Lets you write custom render code for closer access to the GPU. There's a deferred render as a default, as opposed to the forward render that's in the universal render pipeline. Lots of advanced materials that give you very high visual fidelity, and a bunch more great information. Learn more about it at these great sessions that I called out here. So definitely go check those out. It's on the schedule if you want to look it up, if you don't get a screenshot. HDRP is perfect for RTX. So NVIDIA obviously is investing a lot in creating this new generation of visual fidelity, really incredible graphics. DXR, NVIDIA VK Ray, so Vulkan ray tracing, exposes interesting new algorithms. And in order to use those algorithms, you have to be able to create a lot of renderer code that's very custom. Requires a lot of advanced shaders, and that deferred renderer works very nicely with this concept called hybrid ray tracing. So as part of this real-time ray tracing, you can take something that normally you would have been able to do with traditional raster, so you have shadow maps, and you think about like an omnidirectional shadow map, which is like a cube map. You have seams, you have blending issues, you have performance issues. Throw all that away, do it with ray tracing, and then incorporate that as part of your standard raster graphics, and you have a very nice outcome. So there's just a few examples that you could check out there. Dynamic diffuse global illumination, which we're now calling RTX GI. It's going to be something important for Unity. Quake 2 RTX, if you haven't checked it out, it's incredible. Check it out. It's still Quake 2. You know, the core assets look a bit dated, but it's quite incredible to see what you can get away without rendering one triangle. And then Project SOL, Part 3, really cool video, all done in ray tracing. So some basics for graphics debugging. This is Nsight Graphics. It does C++ frame serialization. There's got a resource viewer in it. It does pixel history, API inspection, and you can look at GPU crashes. I'm going to dive into some more of this stuff, but this is kind of a high-level overview initially. It's not just a debugger. You know, RenderDoc is a really great tool. We're a big fan of Balder and everything that he's done, and we encourage people to use that tool, you know, as much as Nsight Graphics. But we also focus on other things that RenderDoc doesn't necessarily focus on, like profiling. And so we have the range profiler, we have GPU trace, and we have the new shader profiler that's in early access for NDA developers that can check out in the pro version. And all of this actually works across many platforms. So, you know, first for APIs, D3D11, 12. We have Vulkan 1.1, OpenGL 4.6 recently supported. We support tons and tons of Vulkan extensions, and every version we come out with more and more. The last version we had 18 new extensions supported. We're going to have new visualizers for those extensions so that you can make more sense of the data. And then as far as platforms, Windows being a primary one, obviously, Linux is becoming more and more of a big focus. Android as well is primarily for some of our embedded development, and then LumenOS. So for Magic Leap developers, you're actually going to be using Nsight Graphics more in the future. And then more platforms that I won't go into, but mind you, this is becoming more of our pervasive graphics debugging profiling technology across NVIDIA. So you have your scene, you want to start looking at it, maybe there's something wrong with it, maybe the performance isn't very good. You need to be able to start with something. And what you need to have is reproducible, consistent. Every time you run it, it's exactly the same. That does not sound like a game, right? So what you can do with Nsight Graphics is you can actually capture the frame and then serialize it to disk. And so effectively, we stop the frame and we capture all the API commands that are actually streaming out, and we save it to a Visual Studio project. And you can actually go at C++ source code. You can actually go and build this project, and you have a replayer that is effectively that frame captured in time. It's just playing over and over again. No CPU overhead, or very minimal CPU overhead. And you can then start your debugging and profiling session on that capture as opposed to on the original application. You don't have to share the original application with anybody anymore. You could just share the capture. You could share it in your team. You could put it in Perforce or Git. You know, it's a bit big, so maybe LFS, but still, there's good places that you can now, you know, open up this opportunity to share this and have it kind of be something that you can coordinate and collaborate with the rest of your team. So, screenshot right there, which shows the connection manager, allows you to launch the application, a bunch of settings and options you can configure, and then finally, once that's all set up, there's interception that's happening where we can actually capture those commands, so we can capture everything and dump it out to disk. Really, really cool feature. Pro tip, unless you need it for performance, run in windowed mode. Much easier to switch between the two. If you do run it in full screen mode, and this applies for a lot of other applications that you might run into this, Windows key tab is your friend. Being able to switch between multiple desktops on Windows at least is very handy. And another quick thing, there is a little bit of overhead associated with the interception for your application. It should be minimal, and we're working every version to reduce that, but do keep that in mind. It's more than noise, so you will see a little bit of a dip in performance. It still is very valuable even with that because you can see the deltas and be able to compare. So, you've got the C++ source code here. Like I said, pretty minimal overhead, and even without source code access to Unity, you can actually see what the API dump it looks like, right? So everything that Unity is doing in its render, effectively you have the equivalent C++ capture. You're not looking at Unity source code, you're seeing at what the GPU is getting. Very, very handy. By the way, real quick on that, this opens up a few doors. You can take the C++ capture and run experiments. You can disable render calls, you can change shaders, you can modify resources. You have all this information self-contained. And so if you have kind of a hypothesis about something, you can go and test it out and run some experiments and potentially even incorporate this into your continuous integration so you can look for regressions and all this great, interesting stuff. You're in Nsight Graphics. You're debugging some stuff, and the first thing you want to look at is your events, right? And events, actions, timings, and markers. So all API calls are treated as what we call events. And we also have actions, which are effectively draws and dispatches. And these translate into like a change in a buffer or render target. And so you can view all of these in the event viewer. You can sort by CPU utilization versus GPU utilization. You can sort by the order and a bunch of great information. You can even, we have a little like mini regex type language where you can actually say, show me every call that's greater than 1 millisecond, right? So you can actually isolate exactly where you're seeing the performance is going. Once you have that, you can also look at the markers associated with the specific workloads that are happening on your GPU. So if you have shadow pass render, if you have water rendering, right? If you have character animation, whatever the workload that you want to subdivide in your scene, you use PIX or NVAPI markers to define that, and then you can actually see that in our what we call the scrubber view. So you can actually see all these markers in their time order. So as I said, PIX markers, NVAPI is also incredibly powerful. In addition to being able to provide additional information into those markers, you get a lot of other great features with NVAPI. If you ever see something like this, don't be sad. You may want to use some of these frame debugging tools. There's some other great options that you have as well. You can look at resources, you can look at shader source code, buffers. We have a bunch of inspectors. I won't go down the whole list. This isn't a tutorial, but there's a lot of great information that you can get just from these inspectors. You can also get the format, you can get the size of the different resources. One of my favorite features is if you have a resource that you write into, like a text or a render target, you can actually see the full number of changes made to that resource. So you might sort by number of changes to a texture, and you'll see that one texture has 300 changes over the course of a frame. Something's probably wrong, or maybe you wanted to do that, but at least you have the ability to filter through that data. We also have a cool feature called pixel history. So effectively, there's like a little cursor that you can just select a pixel in your frame buffer, and it'll actually show you all the events that went into creating that. It shows you the blend states, it shows you the outcome, all the blends, all that information is available in this little view. We're going to be improving that a little bit more in the future too, so that it's easier to select a pixel, because finding the right pixel can be not super easy. All right, you got through the basics. Your rendering looks about right. Performance is not so great. So what do we do? First, I want to mention something. Optimization is not one size fits all. It would be wonderful if there was one prime GPU, and it was the same one on the consoles as on the PC, and you optimize once, and it just worked the same everywhere. It'd be amazing. The reality is it doesn't work that way for many, many reasons that you can guess, but the basic is we make architectural choices that are specific to the kind of problems we're trying to solve. And so you have to take that into account. GCN is not Turing, and I'll talk about that in a second, but the big thing to understand is 71% of gamers out there are probably going to be using NVIDIA GPU for PC. So don't take it for granted, and make sure that you're orienting your profiling needs towards that as well. Not neglecting any of the other people as well, but just do keep that in mind. So this all makes sense, right? A lot of information. I'm not going to go too deep into the Turing architecture. We have some great NDA materials that we can share with developers if you really do want to understand a little bit more about the architecture from a very, very low level. But the basics are, the NVIDIA GPUs are incredibly complex, and they're really good at solving what we call embarrassingly parallel problems. And so if you can subdivide that problem into a parallel nature, it's very, very good at executing on that. Kind of different from the old DX9 days, where things kind of went on a pipeline and was somewhat serial. You're now able to do a lot of work concurrently, and so you're latency bound in a lot of cases. You want to optimize for that. In the end, and this is similar to a lot of the GPU architectures out there, we have these core SMs, these streaming multiprocessors that are able to generalize the kind of data that it consumes and just process anything. So you have, on the Turing, you have 6 GPCs, you have 34 TPCs, so these subdivisions of the way the processors are structured, and the way that a memory is shared between those things, and then the unique hardware in each one of those to accelerate certain operations. So the RT core, for instance, for ray tracing. You then have 68 SMs, and as I just said, 68 RT cores in those SMs as well. So this gives you a lot of processing power, and in the end, what you get out of those SMs are warps, and warps are equivalent to like threads, right? So you have a bunch of these warps that are generated, 32 warps per SM, and effectively these are able to do any kind of generalized work. So they might be shading, they might be transforming a vertex, they might be doing compute work, they might be doing tensor operations for machine learning. Any of this work can be scheduled at the microschedule level at the SM level. So there's a lot of this stuff that you have to consider. I'm not going to go very in-depth into that, but it's good to understand the basic nature of the GPU, just so you understand the kind of problems that you're going to face as you're doing these optimizations. But let's just go a little bit simpler than that. What's the first thing you do when you want to start profiling? Don't run anything in the background. This is the simplest thing you could do. You want a white room or clean room environment. Make sure that there's no interactions. Close Chrome or Firefox or whatever. Make sure YouTube's not running, right? There's a surprising amount of GPU work that these applications do, and this will interfere with the ability for you to get proper results with any kind of profiling that you do. So there's quite a bit of information that you can get from your local machine, what we call a local target. There's also a feature within Nsight Graphics that lets you connect to a remote target. So you can actually connect to a machine that's got nothing going on but the application that you want to debug. Do remote target debugging and profiling. It's very, very fast and allows you to have that kind of environment where you don't have a lot of the pollution for performance. And then, of course, you need to figure out, before you waste any more time, are you GPU or are you CPU limited? I'm talking more about GPU today. CPU is very, very important. Unity actually has some really good tools for understanding that. Perf Analyzer is really good. We also have Nsight Systems, which is a sister product that is more oriented towards CPU and GPU interaction. So definitely check that one out as well. I actually want to mention there's a workflow that we've established to make sure that you're not wasting time and you're kind of moving in the right direction. Start with Systems or Perf Analyzer. Figure out if you do have, if your CPU or GPU limited. Move on to Nsight Graphics. Start getting some basic timing information. You can use the events view, sort by the most expensive things in your scene to kind of validate whether it's what you think it might be. Move on to Range Profiler, so you can actually pick specific ranges based on perf markers, and I'll tell you more about that in a minute. And then move on to GPU Trace and really go low level and get these low-level metrics that provide very specific information about the GPU state at any given time. So, Nsight Systems. This tool is used to help you find resource barriers and fences and other things that can starve the renderer if you're not using it correctly. There's two really cool things I want to mention about this as well. There's actually a frame health and a stutter analysis row that you can actually look at, and it immediately tells you a bunch of great information about whether the stutter is caused by maybe you're compiling a shader in the middle of the frame, or the frame health is not that great because you're doing, you're using the copy engine at the wrong moment, and so you're creating a stall in the GPU pipeline. So definitely check these out. It just immediately gives you some good information on your frame, so there's not much work you need to do there. Are you GPU or CPU limited? some basics here. These are generalizations. Don't just go by this, but this is a good place to start with. If you see lots of gaps between command execution and the GPU sitting idle, you're probably CPU limited. On the other hand, if the GPU work is getting behind the CPU, or it takes a lot longer than expected to be completed, then you're likely GPU limited. If you encounter this situation, it doesn't hurt to actually get an GPU, the Nsight Graphics, and potentially even GPU trace, and you can use some of this data to validate whether you actually are GPU limited or not. So measure twice but cut once. There's a bunch of great tools that we use for profiling. Range Profiler is great for gathering precise performance counters for workloads confined to a specific range. And so you might have a draw call. That's good. You can use that as an action range. But what you're more likely to do is say, show me all the metrics associated with rendering my shadow maps. GPU trace takes it to the next level, which is not just these range boundaries, but potentially the entire frame, or up to 5 frames, actually. So you can if you do workloads that actually span a frame, which a lot of developers are doing now, you can actually see what the performance is from that, the byproduct of that. So you get Turing-specific performance metrics, and you can see all this on a time graph, and we'll talk about that more in a second. And then finally, shader profiler. So you can identify stalls within your shader that negatively impact your performance. And what I mean by that is the way we generally think about optimization or profiling and performance, you're usually thinking like, this takes a millisecond, and I want it to take 0.5 milliseconds, right? And so you look at a shader, and we say, okay, that's taking 0.5 milliseconds. That doesn't really give you enough information to understand what you can do to optimize, especially because of that embarrassingly parallel nature of these GPUs where you can do a lot of things concurrently. I'm going to explain a little bit more what that information is and how the stalls can help you with that. So really quick performance counters primer. Performance counters are very complex, but there's basically a few different categories of them. So you can kind of distill some good information without having to know every single counter that might exist for a GPU, and there are thousands of them, so you probably won't. We sometimes call them performance metrics. Don't worry about the distinction too much. I'll just mention that when we say counter, it's usually like an individual value. When we say a metric, sometimes it's a composite, so it might include a bunch of different counters to generate that. The GPU has different parts that compose the pipeline. So I showed you that really quick diagram of Turing. There's a lot of different units within that. If you look at the Turing white paper, you'll get a lot more information that I won't go into detail here. But TEX, L1 cache, the front end, primitive engine, RT core, CROP, ZROP, all these units contribute to the final end product of where your performance is going. So you want to be able to have metrics that you can grab that tell you the state of those specific hardware units at any given time. So these metrics, they just measure a certain number of things. Throughput, the duration and timing, input-output counts. So you fed this many vertices and this many were actually transformed. Request response counts, stall reasons and those counts of those, and active and elapsed counts as well, or cycles. So let's dive into the first thing that you'll want to look at for these metrics. And so that's the range profiler. So range profiler basically starts by just showing you timing information. So at the very minimum, you have this timeline at the top, and you can start looking at the different perf markers or different actions within events within your scene and seeing how long they took to execute. So my shadow map render took 17 milliseconds. My scene budget is 16. I better figure out what's going on. We also show you memory latency, and there's a lot of information that you can break out. I'll give you this as a pro tip. When you use Range Profiler, there's a little arrow at a bunch of places. Click on that, and it'll expand out, and you'll see some really incredible information about your different hardware units and latencies. This allows you for action ranges to be selected, and you get the performance counters for those specific regions as well. So when you run it, it'll actually sit there kind of processing for a while. What it's actually doing is statistical sampling and giving you a final byproduct out of running the frame multiple times effectively. So it's always running that replay. You can export this data for diffing or for additional analysis. So you get a CSV, you can store that off. You can do nightly runs if you want to, where you can see how this data is evolving over time. And then this is really cool. You can actually edit shaders within Nsight Graphics, do another range profile to see what the result of that is. So you can create a good iterative development cycle that allows you to see if you made some minor or major changes, what the outcome of that would be. GPU Trace is kind of the next level. It's our next gen profiler. It's akin to some console tools that are out there, and it's really incredible because it gives you a lot of very great information visually. So it's a more of an intuitive tool. You can look at some of the data and make sense of it just by looking at it really quickly. So it uses special Turing features to gather that detailed timing information and gives you those performance metrics into what we call the metrics graph. So basically, we lay all that out into a graph that you can look at for over the course of the frame, effectively the throughputs or the values of that. So you get statistics on GPU throughput. You can get trace data for multiple frames. Traces are savable, and you can annotate them. So this is pretty cool. It's not like the other thing where it's live or it's replaying. You could save this off, and then you just have a file, like a flat file, and you could just hand it to somebody else. They could look at it. You could select a region, and you can leave a note there. So you could say, this looks strange. I don't know why you're getting 17 milliseconds for your shadow pass. You can leave a bunch of additional information, share that with our dev tech, right? It's very useful for being able to pass that information around and try to understand what the problem is. And then this is really cool. We actually have diffing via something called trace compare. And so you can actually take either two traces or the same trace and any of the frames within it, and you can compare that and see them kind of overlaid over each other. So you could see what the difference might be if you used a smaller shadow map buffer, for instance, to see if that actually affects the performance positively or not enough. This is something that we haven't released yet. This is pretty cool. This is the shader profiler. And so we are sharing it in the pro version. It's an early access. If you're a professional developer and you want access, just contact us, let us know, and we can get you access to that. I'll share more information about that towards the end. But effectively, it's PC sampling based. It's similar to the range profiler where it's running on a frame that kind of runs and repeat, and it uses all these samples to determine how many samples passed and how many were stalled. And so you get a summary of all the shaders, and you also get all the hotspots, so the places where you're getting the most number of stalls, and which specific instruction. So this is under the instruction level where you're getting the most number of stalls. And so this is used to optimize latency-bound shaders. And so you can save one of these sessions off and be able to analyze this after the fact or share it with people and have that information readily available. Really quick, I want to mention the big thing about stall reasons. Why does this matter? Why is this important? I'll give you a quick example. You might have a texture. So let's say you have a shader and you sample texture and you want to do some kind of blend operation and then output that. You have to do the texture sample and then maybe a multiply at the bottom. And so what might happen is you start the texture sample, but the GPU is smart enough to kind of pipeline things and knows how to do a bunch of instructions and kind of schedule them in a way where it can hide a lot of that latency. It's all about hiding latency, right? Now, what might happen is that texture operation takes a really, really long time to finish. And so here you get to this blend operation, and maybe the GPU is sitting there now saying, I actually can't get past this point. I need you to finish whatever you're doing so that I can complete this operation. This is a stall. There's a lot of different reasons for why that stall might occur. The one I just talked about is something called a long scoreboard stall. And effectively, it's just sitting there waiting for the L1 text memory operation to complete so that it can transfer that texture into memory and then complete doing the arithmetic operation on the two values. So it effectively just sits there waiting. When you can identify that, when you're making these shaders and you see that you're doing this kind of stuff, you can go back to that texture and you could be like, is it too large? Am I doing something weird with blending? Oh, I forgot bitmaps, right? There's all these things that you can now take steps to try to address. There's a lot of complexity. There's a lot you have to know to make sense of what a long scoreboard might mean. That's one of the things we want to improve in the future and make a little bit clearer for people. So, next-gen graphics debugging. So, real-time ray tracing in 1 minute. Really quick. Let's see if I can do it. Obviously, it's performance heavy. DXR Vulkan ray tracing is accelerated on Turing GPUs. We have specialized hardware that will accelerate the tracing operations. The way that the whole thing works is basically there's BVH, bounding volume hierarchy, that serves as an acceleration structure, and there's two levels, top level, bottom level. We usually call them the TLAS and the BLAS, or the BLAST. Shaders and resources are configured up front. People are familiar with the bindless model. It's kind of like that. But effectively, if you're going to trace array in the scene, it can go anywhere. So you have to make sure everything is loaded and set up properly initially. This can be challenging if you have a streaming world, by the way. There's a call in DXR, it's called dispatch rays, and Vulkan, it's trace rays. You send a bunch of rays onto the scene. There's a shader called a ray gen that effectively starts shooting all these rays into the scene. And then determines, there's a bunch of additional shaders that determine whether they refract or reflect, or there's recursion involved with it, all these things, right? And so in the end, you get this final byproduct that is the output of that. So it might be a buffer or a texture, whatever you want. So if you're going to do reflections into the scene, you have your world state, you have the shader that generates the rays, you have the one that reflects it, and then the final output color that goes to that buffer. Now, this is all interesting. Some of you may be working at DXR, some of you may not. How many are working in DXR stuff? Okay. For people that didn't see, there's like 2 guys. That's okay. What I expect to see in a year or 2 or 3 is everybody, because the next generation consoles are, there's hints that they're probably going to support it, right? And if HDRP and if the high fidelity rendering is what you're moving towards, you're going to have to consider how this technology is going to be a part of the systems that you're creating. I'll tell you, it's probably going to simplify things. The situation I mentioned before about the QMap render for omnidirectional shadows, those kind of hacks disappear when you're able to just shoot a ray into a scene and get shadows. So it's a good thing. Start early, start understanding how this technology is going to be important to you now. And the right there, by the way, it's just kind of an overview of how everything is configured with the top level and bottom level. And there's a binding table that you have to use to configure all this information. I anticipate most of that will be handled by Unity under the hood. But if you are doing custom code, you do need to understand that stuff. What we have for debugging that, really powerful feature, we had somebody open this up and almost immediately find a bug. Not in ours, in their implementation. We've had performance issues also addressed really quickly with this. So this works for any real-time ray tracing API that's out there right now. Quick verification of BVH before you even start tracing rays through the scene. You can see about alignment of axis line bounding boxes with your blast. There's actually an edge case condition where you want to make sure that your bottom level acceleration structures are axis aligned. You'll get a performance benefit out of it. There's geometry flags, so you can actually define if an object is opaque or translucent. This is important because imagine the scenario where you trace a ray in a scene and you hit a translucent object. That ray's got to keep going. Well, guess what the default value is when you trace rays? It's the one that doesn't cause rendering errors, which is translucent. So everything just goes through everything. What you want to do is you want to find your solid geometry and immediately make sure that it's set to opaque. Otherwise, you're just throwing performance away for no reason. We've seen this quite a bit, believe it or not. You could look at buffers and transform data, and then a bunch of stats like the instance ID, number of instances, number of primitives. Volume size is pretty important as well, because obviously the bigger an acceleration structure takes in the scene, the more likely a ray is going to hit it and cause transform data to have to occur and performance implications. We have an API inspector for ray tracing as well. This works for DXR and VK Ray. You could look at that shader table. I mentioned the ray gen, any hit, miss shader, all the different shaders that you might run. You can actually look at the source code of that within the inspector. You could look at constants, uniforms, samplers, buffers, all that information, and then the acceleration structure as well. We actually show you the one that's associated with the dispatch race call, and you could just click on it, and it'll open up in its own viewer. Now I'm going to tell you, all this stuff is super cool, right? It's amazing when you can have real-time ray tracing working in your application. None of that matters if the first thing that happens when you run your application is a crash. And so traditionally, CPU crashes, there's been some good tools. We can get core dumps. There's lots of information that we can get to try to identify what's going on. For GPUs, there's been nothing. Nsight Aftermath is hopefully the answer to that, where we actually have GPU crash dumps that are available to developers now. Nsight Aftermath It's kind of an evolution of some work that we'd been doing for quite a while, and the current version is really, really interesting because you can take those GPU crash dumps, open it up in Nsight Graphics, start looking at the GPU state at that given time, look at the shaders associated with the crash. So or I should say the TDR. So you might have had a timeout because you did an infinite loop in a shader by accident. So when you're writing your custom shaders, because you're now in HDRP land, you have to consider that you have more opportunities to make these kinds of errors, and you want to make sure you have a good tool like this set up to catch that. One really, really cool thing about the latest version that we're going to be releasing as part of something called the Nsight Aftermath SDK is you're going to be able to bundle Aftermath with the user application. And so when there's a crash on your user system, you're going to actually be able to get that GPU crash dump, attach it to the crash reporter, and then send that back to home base for logging into a database and data mining and whatever you want to do with that data. This is incredibly cool because if you think about it, you might have a few dozen QA people or a few dozen programmers on the team. You're going to have millions of users, hopefully, that are going to potentially encounter these issues. And there's some cases where you're just never going to see it until it's out in the wild. This finally gives you an artifact that you can use to try to understand what was happening there. So, what's next? Nsight Graphics and Unity. We got some work to do from the graphics tools team. There's quite a bit we want to do to make sure to create a better experience there. Better launching connection to Unity apps. So, right now, there's two ways that you can launch Nsight Graphics with Unity. You could do it through the editor, and then when you launch, when you start the game mode, you can get the API calls directly there for interception. So it does work properly. The other way is to create the standalone application, which is the only way to do GPU trace. And so there's a lot of work that we need to do to integrate it better. Yes, I've heard from multiple people, it'd be great if you had like a render doc-like button. Yeah, we've heard you. We're going to be working on that. So that's the next part as well, better integration with Unity Editor, making Nsight Graphics first-party tool that can actually work really closely with the editor and provide a lot of this great information. And then finally, mapping between shader graph and generated shader. So there's the custom shaders you're going to create, and then there's just the shader graph, and there's still the ability to create some custom stuff there that can be problematic. And so we want to make sure that we can map between the two. Shader editor is not going to become part of Unity Ed, but at the same time, we do want to make sure that we can map the data back and forth so that you know which material might have caused a particular performance degradation. And finally, we have a new feedback button, and please use it. It gives us screenshots, system info, and detailed feedback on issues or feature requests that you might have. We will not submit any of that data if you don't want it. You don't have to put your email. It's completely anonymized, so if you're worried about privacy concerns or anything like that, if you put your email, we will contact you, though. We promise we read these, and they're very, very important to us, and they're the best way for us to know what we can do to make your life better. So, Nsight Graphics Pro, there are a lot of professional developers in here. I want to make sure to let you know that there is a special version of Nsight Graphics, akin to what you might see in console development where there's like a program for access to some of those tools. This tool has, first, access to early beta features that we are still getting to a good state before we release. The shader profiler is a good example of that. One of the reasons why we haven't just released it is because we got a bunch of developer feedback, and we're now realizing, you don't want to have to close the whole application and go back and then make changes and then go and shader profile again. You want to do it all in the same place. So we're making improvements to that. This is one of the big reasons why we want to make sure to share this stuff early with developers and get things to a good state, give you an opportunity to actually influence the development of these features. SAS assembly, so SAS is effectively shader assembly that's executed directly in a GPU. It's very, very low level. You can actually see how the DXIL or SPIR-V is translated into optimized shader assembly, and the compiler does a lot of optimizations and interesting things. Being able to look at the SAS directly from your shader source code is really critical. You also get NDA counters that we don't normally release. So you'll see counters for hardware units that you didn't know existed because we don't broadcast it. Which brings me to the NVIDIA GPU programming guide. There is a special guide that we share with certain developers. You'll need to request access and sign an NDA, but If you worked with us in the past, you probably already have access, or it's very, very simple and straightforward to get access. You get a lot of unreleased information on our architectures, including some NDA sessions that we've done in the past to try to explain more of the life of the modern triangle to developers. Future versions will also provide more information on the counters and metrics that exist and how to use them. So a lot of that information, like I said, is very complex and maps to those specific units, and this is going to give you a lot of really great information on that. Nsight Graphics Pro Reference Guide. So here's this tool, here's the manual on the GPU, go, right? Doesn't work that way. What we decided to do is create a reference guide that can map between the two. So you have a concept in the tool, you have a concept in the GPU, and this is kind of the bridge between the two, so you can actually see what that translates to. So a lot of background on the data. We're going to talk about workflows and how you can do best practices based on information we've gotten from our dev techs, the developers that actually work with developers to bring these optimizations to their applications. And then we also talk about some features that we wouldn't normally be able to talk about. So we go in more detail about SAS, and the hope is to expand more on that and show what the SAS assembly instructions actually do. Because we do have some special SAS assembly instructions. And then we have a program called PID, or GRS, Game Ready Services. Again, if you need access, contact your content manager, your dev tech, or send us an email, and we'll just get you in touch with the right people to make sure you can get that. Learning more, check out these previous sessions. The slide will be, deck will be online later, so feel free to just get this, and you can get the links and just look them up online. What I'll mention, we do have some good ones, but definitely check out those sessions from Louis Baval. He is a brilliant dev tech engineer who actually shared his own development process that he uses as a dev tech for profiling and optimizing AAA applications. He's done this for many, many big games that you probably would know about, and this is effectively his process for that. So just to wrap it up, HDRP provides great flexibility, but with this, some potential performance cliffs. You need to look out for that, and you need to use the tools to make sure that you can validate as you're building out your renderer. If you're going to learn more about HDRP over the next few days, just keep that in mind as you're listening to all this great new information. Profile early, profile often. Never blindly optimize. Know where your money's going. If you think it's the shadow render, because shadow renders are always expensive, you're going to just waste time going down that alleyway without really validating, am I getting 20% of my performance back? What's the potential maximum that I can get? If you can see what your throughput is for your, or your GPU occupancy is for a given workload, you can actually see if you're utilizing the GPU effectively for that or not. You can also see if you're underutilizing. So if you could be doing more parallel work, asynchronous compute, or other operations, you'll see that you have a little bit more to work with. Sort effort by most expensive workloads. So find out what's the most expensive thing. If it is a shadow map render, look at that first. As a percentage, you're probably going to find the bigger rewards from that big one. If it turns out you've optimized it and squeezed every last bit of water from that stone, move on. But always keep that in mind. As you change things in your renderer, there's potential for other issues to bubble up. So don't just pass it by. Next-gen features need specialized tools, so nobody else is going to make those DXR NVIDIA VK Ray tools. Variable rate shading and task and mesh shaders are huge new things that are coming online. You want to make sure you can properly debug those, so this is the best way to do that. Last thing, Nsight Aftermath is coming into Unity. So the thing I told you about for getting your GPU crashes from the user, we're actually going to provide a plugin that's going to allow you to include that within your application. So we'll have more information about that soon, but expect something in the last quarter of the year. So big thank you to Lydia White, Mark Gerberman, Chad Vivoli, Jeff Keel, Don Alfaz, Alatham, Paul Hodgson, Keith Hollicky, and Sebastian Domine for making this possible. Thanks again to Unity for having us here. And thank you. So I have some links here. I think we only have like a minute for questions, so I'm not sure how we want to handle that. I do want to, before everybody leaves, there is one last thing. With the questions, I'm going to give away one copy of the real-time ray tracing book to somebody who can answer a question of mine. So can we start? Do we have questions? All right, I'm going to ask a question. Whoever answers it right gets a book. In what year did Turner Whitted introduce the concept of recursive ray tracing to the world? What? Almost. More. Keep going backwards. It was a long time ago. It wasn't 73, but you're getting closer now. Oh my gosh. All right, who said 81? 81? It was 79. You came closer, so I'm going to give it to you. Hold on, I'm going to give a ruler away too, a follow-up question. What is the code name for the NVIDIA GPU architecture that introduced programmable pixel shading? Huh? CG was the programming language that evolved to HLSL. This is the code name for the NVIDIA GPU. I'll take the NVIDIA GPU, not code name, the product name too, if you can guess it. What's that? It is a GeForce. Which GeForce? No. Huh? Who said that? GeForce 3. You got it. That was the NV20, by the way. I'll give you a ruler. Come up here. I'll give you a ruler and then a book to you. Perfect. All right. Thank you very much.